Okay, we can start cutting the video now. Okay, so we'll have lecture 3 now, like I wrote down. And I just want to say a word about the exercises that I posted for lecture 2. There were 2 typos. I think most people found them, but just in case you were really stumped on a problem, maybe it was my fault, so you can look at them again. And then I realized that some of those combinatorial arguments were a little harder than I expected. That's the kind of thing the book's like, you just count. And I was like, yeah, I know how to count. But then when you actually count, you're like, oh, counting is difficult. There's many numbers. And so I added one problem that kind of leads more into those counting problems. But they're kind of difficult. So I think it would be okay if you just worked out some examples and convinced yourself that it were true and did not get full proofs for the dn and the ln. Really what you need is the degree of dn to prove that the thing converges everywhere. So anyway, and if you haven't been doing that, then today when I talk about dn, you will be so confused and it will be so sad, so do your exercises. Okay, but today I will start with additive and FQ linear polynomials, which are the last kind of machinery thing we need before we can finally talk about modules. And the reference that I've been using for this, there's terrible glare, is Basic Structures of Function Field Arithmetic by David Goss. It is not the fun stroll in the park that Gouveia is. You will probably not stay awake until 3 reading this, except if you're banging your head on a proof like I was last night. But it is one of the most complete books on Drinfeld modules, goes much beyond modules into stukas if you want to learn about them. And it has a lot there. And Goss was a great expositor and mathematician. So I recommend also this book. And if you click on the right Amazon link, I get a commission for every book you buy, so that's not true. Okay, so let's do this. So last time I introduced the definition of additive. I'll just repeat it because it's already been 24 hours. So I'll have K be a field and P a polynomial with coefficients in that field. And I'll say that P is additive. Okay, and I really should say, I didn't last time, but say something about the field, because I will define it in this way. If P of alpha plus beta is P of alpha plus P of beta for all alpha and beta in that field. Okay, and so this is very K dependent. As you can see with the example that I gave last time, if you played with it, okay, this is additive over F3, but it's almost like a coincidence, if you go to F9 or any other field of characteristic 3, that wouldn't be the case anymore. So, you're kind of cheating. Right, and so maybe that's not the best definition of additive, but that's the one Goss gives, and that's the book I'm following. And besides, I don't care about finite fields, so it's not that big a deal for me. But maybe a better definition is P is absolutely additive if same equation, P of alpha plus beta is P of alpha plus P of beta, but now you say for all alpha and beta in the algebraic closure of the field. And that's always infinite, so that kind of takes away some of those tricks that made that previous polynomial work. So this polynomial here would not be absolutely additive over the algebraic closure of F3. This doesn't work anymore. So finite fields, by being finite, they kind of cute their way into stuff, but it's not really true. Okay, so what I want to do is focus on absolutely additive polynomials, or infinite fields, it'll turn out to be basically the same idea, and characterize those polynomials, right? Like what do they look like? Where can I find them? And so for that, I'll just need a little bit of setup. So I'll have another definition. Okay, so let K be a field of characteristic P. I said this last time. I should just move back. In characteristic 0, additivity is very boring because it's just being linear. And so you would be talking about even lines that go through 0, and the lecture would be over. Okay, so let's go in characteristic P, where interesting stuff happens, right? Because we have raising to the P that's linear. So you're like, oh man, many things will be, are additive. So many more things will be additive. Okay, so let K be of characteristic P from now on. So there's something interesting to say. And I'm going to define tau sub P to be x to the P. Then I'm going to define this this thing. So it's like K brackets T, except I use curly brackets, and the curly brackets is because that's not going to be commutative. And as a vector space, to be the space spanned by tau to the 0, which is x, tau sub P to the 0, tau sub P, which is x to the P, tau sub P squared, which is x to the P squared, etc. Right? So it's spanned by just these monomials. So I'm restricting, inside the space of polynomials. So I'm going to look at polynomials, but only polynomials that have terms like x, x to the P, x to the P squared, x to the P cubed, etc. Not any of the other exponents are okay to happen in this space, like just right now as a vector space. Okay, and I guess I'll do this on the next page. Okay, and then this is an exercise. This space is a non-commutative ring. With the addition from the polynomial ring, so just like add polynomials like normal, okay? But the multiplication in that ring is composition of polynomials. So I'm not multiplying the polynomials like normal. I'm plugging one polynomial into the other. And maybe here this explains my notation. Here when I wrote TP squared, right, I didn't mean like x to the P times x to the P, which would have been x to the 2P. I meant x to the P inside x to the P, which is x to the P, which is x to the P squared. So now this kind of explains this notation. Okay? So I just like really want to stress that T sub P to the I, that's x to the P to the I in this ring, because the multiplication that I'm writing on the tau is composition on the kind of x world. Okay, and then as another definition, I will also have later, I call it tau sub P. If I let tau be x to the q, then we can similarly form k twisted brackets tau. But this time I would only allow the monomials x, x to the q squared, x to the q cubed, x to the etc. And it would still be a non-commutative ring with composition as its multiplication operation. Okay, so I'm going to start by talking about this ring for additivity and then this ring for FQ linearity. It's kind of, additivity is a difficult part of the, like, not that any of this is like very difficult, but we'll start with like proving like additive stuff. And then when we want FQ linearity, we'll like just soup it up a little bit to having this ring instead. And this is, at least like Gauss calls it, and I've heard it call it a twisted polynomial ring. Because it kind of looks like a polynomial ring, but it's not, because it's not commutative. Okay. Okay. So then, why did I introduce this other than to confuse you and introduce more brackets into our lives? Is because of this proposition. Let K be infinite. So I'm going to move away from that finite field nonsense where stuff happens that I don't like. Then P is additive over K if and only if P is an element of this twisted polynomial ring that I defined. So right now, I mean, you might think, like, why did you go through the trouble of making it a ring? That payoff will come later. For now, I'm just saying, right, if the only exponents that appear in P are, x to the 1, x to the P squared, etc., that's the only way to get an additive polynomial for an infinite field. So, this, my first example, that violated that because I had x to the 6, 4, 2, and 1 over F3, but that's because that was a finite field. If I have an infinite field, then this would not work. Where was I? Okay. So for the proof, I'm going to need two things. Okay, so two ingredients to the proof. The first ingredient is that the map from the algebraic closure of K to the algebraic closure of K, and K is of characteristic P. Okay, sorry, of characteristic P. From now on, I'm always in characteristic P. Okay, so same K, infinite of characteristic P, but now I want an algebraic closure. So the map sending x to the 1 over P is a field automorphism. Okay, and I'm not going to prove this to try to speed up and actually get to Carlet's modules, but basically you would prove this by showing that x to the P is a field automorphism. And then its inverse is also a field automorphism. Okay, and how you would do this? Well, this respects multiplication because it's exponentiation. That would always happen. It respects addition because it's raising to the P. And so all you need to prove is that it's bijective. But you get the bijectivity from the fact that this is algebraically closed, so everything has a Pth root. Okay, so I'm not going to say more about this. And then the other ingredient is the derivative, which you know and love. If P of x is n is equal to 0 to big N, an x to the n, I'm going to let P prime of x be the sum n is equal to 0 to big N of n an x to the n minus 1. Okay, so no surprises there. That's the derivative you know. Because we're a field of characteristic P, so I don't want to define this with like a limit and things like that. I'm working with polynomials, so I'm just going to define it formally by moving the exponent down and lowering it. Okay, so I'll be using that, and I didn't want you to worry. Okay, so let's prove this, right? So the proof that P is additive if and only if it's in that ring. Well, okay, one direction, this direction is easy. if P is in this twisted polynomial ring, it is additive, since x plus y to the p is x to the p plus y to the p. And this polynomial ring only has, like linear terms and to the p squared and to the p cubed. So that's not the problem, right? The problem is that this is the only way to get that. So assume p is additive. And now I want to show that it has only these kinds of monomials in its expression. So I'm going to fix some alpha in my field, and I'm going to look at the polynomial p of x plus alpha minus p of x minus p of alpha. Okay, this has infinitely many roots. Right? Any element of, here, alpha is a constant, but x is an indeterminate, so this is a polynomial in P, and whatever I plug in from my field, which is infinite, I get 0, right? Because my polynomial is additive. So a polynomial that has infinitely many roots has to be identically 0, which I'll denote with this 3 bars, right? So this is the 0 polynomial because it hasn't. So that's where I use that my field is infinite. Okay, so then I get as a polynomial equality. Okay, the not surprising at all fact, but now this is a polynomial equality, right? In my definition of additivity, the x and the y were elements of the field, and now I've kind of souped it up one to having a polynomial equality with an indeterminate. So that's the significance here of what happened. And so these are equal polynomials. What I'm going to do is I'm going to differentiate both sides and plug in x is equal to 0. Okay, so on this side, if I differentiate, and I plug in x is equal to 0. Okay, well, if I differentiate, I get p prime of x plus alpha times 1. Chain rule, right? Still works. Okay, but then I plug in x is equal to 0. So that's p prime of alpha. And on this side, if I take the derivative, it's even easier. And I plug in x is equal to 0. Well, that's p prime of x. That's a constant. Its derivative is 0. So that's p prime of 0. So what I get on either side, right, is that for any alpha in my field, the derivative at alpha is the derivative at 0. So the derivative is a constant. And if we were in characteristic 0, that would mean that p of x was, some constant times x. But we're in characteristic p, so it doesn't mean that. Okay? It means that there's a bunch of other terms, but nj is always 0 mod p. Right? So I've won a little. I know that the monomials that appear in P, at least, except for the linear term, which is cool, at least the exponents are 0 mod P. They might not be powers of P yet, but at least they're 0 mod P. Because then when I differentiate, right, all these little n's come down and they're 0 mod P, so all that stuff goes away. And then the derivative of the Cx is the constant. That's the derivative of all the other points. So I'm halfway there. It's not really half the numbers, but I'm some of the way there. So now I'm going to write my P as P naught of x plus P1 of x with P naught of x in my twisted polynomial ring, right? So of all these exponents, some of them are powers of P and some of them are just multiples of P that are not a power of P. So I split them up. I put the good ones here, the powers of P here, and the bad ones there, the ones that are just multiples of P. And what I hope is that P1 of X is 0, right? That's what will be enough. And notice that P1 is additive itself because P1 of X is P of X minus P naught of X. And these two polynomials are additive, right? This one is additive by assumption, and this one is additive from being in this twisted polynomial ring. And if you work it out, the sum or difference of two additive polynomials is also additive. So I have an additive polynomial, right? So now I'm going to let P to the E be the largest power of P that divides all the exponents of P1, right? So maybe it was like 2P, 3P, then that would just be P, but maybe it was like 2P squared, 3P squared, and then P squared would be the largest, just like the whichever one, right? And I'm going to let P2 of X be P1 of X to the 1 over P to the E. And now I win. Okay? So this is still additive. Because 1 over P to the E, raising to the 1 over P to the E is a field automorphism. So you can work that out, right? Because P1 was additive, then raising it to the 1 over P to the E respects all the field operations, in particular addition. Okay? But P2 has an exponent that is not 0 modulo P. Right? Because any power of P that divided all the exponent, I took all that out by raising to the 1 over P. So now I'm left, if it was like 2P squared, 2P cubed, I'm left with like the 2 and the 3. Right? If I'm left with only powers of P, then it means they were just powers of P to start with. Okay? So now, by my same argument before that I applied to this additive polynomial P, then this means that the sum had to be 0. And actually, then this one also couldn't have been there because I assumed that there was not just powers of P in there. So I win the game with this polynomial. Okay, so P2 has an exponent that's not 0 mod P if it's not 0. Of course, if it's the 0 polynomial, then I just did this to 0 and nothing happened, and that's fine. But if there was anything in P2, then I got a contradiction. So I'll try to fit it in here. You guys still see that? Okay, so P2 of X is 0, and so my P is in this twisted polynomial ring, and my proof is done. Okay, so it's kind of a cute argument. This whole part of the course has really adorable little arguments, I think. Okay, so from now on, we'll assume K is infinite of characteristic P, because I will certainly forget to say it. Okay, but I only care, like really in my heart, about FQ brackets T, which is both of these things. Okay, so we'll need one more definition because I'm in characteristic P, a polynomial. It's a definition / proposition. A polynomial is separable, so this is over any field if its roots are distinct in K bar. Okay, so that's if you took like any Galois theory or abstract algebra, that's the usual definition of being separable. And this is the case if and only if the polynomial p and its derivative p prime are relatively prime. That, again, is a standard fact of abstract algebra in a field of any characteristic. And it's an exercise to prove it. If you've never proved it, like you should. You can't not prove this. But for me, what I like about this criterion is that if I have an additive polynomial, the derivative is very simple. I'll let you figure it out. And so it's very easy to tell if an additive polynomial is separable or not. So that's an exercise to give like a lightning fast criterion for an additive polynomial to be separable. Just think about it a little bit. And so everything is very nice in this setting. Okay. And so now we'll come to the fundamental theorem of additive polynomials. Which is the whole point that I was trying to get to, and which I will use all the time, and so should you. So let P be separable. And I'm going to denote its roots to be W1 through Wm. Okay, they're all distinct. So this is a degree M polynomial because all the roots are distinct. Then, and I'm going to call this set big W. Then P is additive if and only if W is a group under addition. What? This is very surprising at first. If you're not surprised right now, let me tell you, you're surprised. And very cool. So I have a polynomial, it's additive, that was kind of fun. But now if I just take its roots, I get a group out of it. Like I can add two roots. So first, you can add two roots and you get another root. That's not so difficult if the polynomial is additive. But the other way around is like whenever you can add roots and get another root, your polynomial is additive. So that's very nice. So let's prove this because it's also a really nice polynomial argument. Okay, so again, there's one direction that's easy. I think this one, right? If P is additive and W1, W2 are two roots, then P of W1 plus W2 is equal to P of W1 plus P of W2, which is 0 plus 0, which is 0. So the roots are closed under addition. So let's do the other side. So for the other side, it is enough to show that this polynomial is additive. Right? Because my polynomial P that had these roots is just a constant multiple of it. And if this one's additive, then a constant multiple of it is additive too. So I'm just going to work with this one. I'm going to show that it's additive. And I'm going to notice that if I have a root, then P of x plus W is equal to P of X, because adding W to X is just permuting these roots in that product. So it's the same product. And now I'm going to do a really tricky trick. So I'm going to start by fixing Y in my field. And I'm going to let H of X be this polynomial. Okay. So again, I'm using my thing where like Y is a constant and X is an indeterminate. So I'm playing that game. Okay. So this is a monic polynomial, right, of degree M. And this is a monic polynomial of degree M. And so the first term cancels. We talked a lot about canceling, right? So the degree of H is strictly less than the degree of P, which is M. But every little w in big W is a root of H. Because if I put a little w here, I get PW of W plus Y. And then PW of W, that's 0, because it's a root. And then PW of W, of Y, right? So I get exactly this. I get this one is that one, and this one minus that one, so there's 0. Okay. I would switch page to like work it out, but I don't think that would be more clear, right? But the point is that this one is going to be equal to that one, and that's going to be 0 when you plug in W. So I have H of degree less than M that has M roots, or I've just exhibited M times where it was 0, so it has to be identically 0 as a polynomial in X. Okay, so I said I was going to be tricky. That wasn't so tricky. Now I'm going to be tricky. Now I'm going to let Y be an indeterminate. So I'm going to call this H1, so we're not confused. But it's the same. It looks the same. It's not the same, but it looks the same. Right? This is now a polynomial in 2 variables, X and Y. I'm not using Y an element of my field. Okay? And if I plug in alpha, right, if I plug in an element of my field, then I'm back in my earlier situation. Right? Here when I was like, oh, Y is an element of my field, I was like, oh, that's a polynomial that's 0 in X. So now I have like a polynomial in Y, and I plug in any element of the field, and I get 0, right? I get like as a polynomial, so maybe I want to really think about it as like a polynomial in X in Y, right? So the polynomial in Y has infinitely many roots, so it has to be 0 as a polynomial in Y. And K is infinite. So that's the tricky part. So H1 of Y as a polynomial is identically 0. And so now I get this identity as a polynomial identity. And so P is additive. PW is additive. Okay, so there's like just some delicate stuff with plugging in elements and thinking of polynomials. 0 is polynomials, or 0 when you plug in. And I invite you to ponder this deeply if you were not convinced by my argument now. So this was all about additivity. And I want to upgrade to FQ linearity. And I'm just going to state the results. They're actually easier to prove, so I'll leave it for you to do. So upgrade everything to FQ linearity. So the definition is P is FQ linear if it is additive and P of zeta x is equal to zeta tx for all zeta and FQ. And that's as polynomials. So last time I said for every element in the field, but actually you can say it as polynomials. So if it's additive and you can pull out an element of FQ, that's exactly what you need. That's like what's usually meant by FQ linearity. Okay, and then the analog of this proposition that we had that characterized these polynomials, right? For additive, they had to be in K curly brackets TP. So here we'll have P is FQ linear if and only if P belongs, but this time it'll be K brackets tau, right? And remember that tau is x to the q. So the x to the q will respect the addition, and then raising to the q will allow you to pull out an element of FQ because elements of FQ are fixed by raising to the q. So that's the proof of this. Okay, and then the fundamental theorem, I think I can fit it on this. Is let P be separable, W its roots, right? Same setup as before. It's separable, so it has M roots. During some algebraic closure, that's fine. Then P is FQ linear if and only if W is an FQ vector space. Okay, so that's also awesome. Okay, and the proof is very much like the other proof. You make like some H polynomial from this relationship, and then you argue that it has like degree less than M, but M roots, so it's identically zero. It's like the easy part of the argument for additivity, for the fundamental theorem for additivity. So you can just think about that. Okay, so we'll use this some, and also these are kind of fun facts. Like to me, I mean, in characteristic zero, right? I mean, you have a polynomial and it has roots, and okay, they generate, field extensions. Maybe you care about that, but like the fact that the roots, like as themselves, have an algebraic structure, I think is very cool, and that they can be, like a vector space, like just themselves, just the roots of a polynomial. Like I think that's nice. Okay, we're finally ready, you guys. So. Remember my analogy, right? I had the polynomials were my integers, the rational numbers were my rational functions, my reals were these giant series, my complex number was this field C infinity, which if I denote this by K infinity, this is K infinity festooned with hats. And then I said people write pages and pages and pages of stuff on the left and stuff on the right. So today, I'm going to tell you one thing that can go on the right if you put the exponential function on the left. And I say one thing because it's not really a one-to-one correspondence. A lot of the time in function fields, different things play different roles or different aspects, right? Like the exponential function is this like many-splendored thing. So many different things on the function field side might play its role. So I'm going to start with a classical interlude of telling you what do I care about with the exponential function that I want to emulate on the function field side? Like there's some specific thing that I want from this exponential function on the function field side. Classical interlude. So I'm actually not going to write e to the z a lot of the time. I'm going to write the exponential of z. And I'm going to give it by this power series, z to the n over n factorial. That's how I choose to think of it. And if you did the homework, you saw like e sub c was z to the q to the n divided by dn. You should see a parallel there. And that will be the parallel. That's how I will start the Karlitz module with an exponential function that has a similar expansion. And you might notice, you hopefully have noticed by now as a mathematician that, and now I'm going to go back to the e to the z notation for a second. E to the nz is e to the z to the n. Okay, and if you've been a TA, then you try to pound that into your students' heads. Okay, and e to the n plus m z is e to the nz times e to the mz. Another thing that you might struggle to get your students to accept. And so what I want to point out by this is not exponent laws, but how on this side, multiplication by n becomes exponentiation by n, and addition becomes multiplication. And so I've said this before, and hopefully you've thought about this before, right? But on this side, I'm thinking of like the additive group, and on this side, I'm thinking of the multiplicative group. And you can think of like exponentiation as going between like G and GM, right? The additive group and the multiplicative group of your field. Okay. And so I'm going to set up a diagram that I will set up again for you in the Drinfeld setting. And I'm actually going to think of the exponential function as going between c and c cross, the multiplicative group of c. For one thing, that makes it surjective because I never hit 0 with the exponential function, so I might as well not worry about it. And I also want to remember that on this side, when I add, right, on that side I multiply. So I think of multiplication here. And on this side, right, I'm going to think that I multiply by n, and then when I exponentiate, right, the right thing to go here is the map z to the n, right? And that's it. That's the whole point. So here I have one action of the integers, right? I can think of z acting on the complex numbers by multiplying. And here on this side, I have another action of the complex numbers, z acting on c cross, but this time by exponentiation. And for us, it doesn't feel like a new action at all, right? You're like, I like multiplying and exponentiating equally. It's not that new. But in the Drinfeld setting, the action that we'll get on this side will be a little weirder, so maybe a little newer to us. So that's why I'm like starting you out easy with something you're not too sad about. Okay. And I'm going to rush to the punchline. Well, okay, no. So sorry, I should say this, right? So the exponential function gives, and I'm being a little wishy-washy here because on this side I have c and on this side I have c cross, but c, a new Z module structure. Which, if you don't know what a Z module structure is, that's what I just said. Like one way to act by n and another way to act by n. Or like an element. Okay? Why do we care? I'm happy you asked. It is a theme that if you can think of a smart action, a smart new action of your integers, and you look at their torsion points, you will get really good field extensions. So let's look at the torsion points of this new action. I mean, new in quotes. It's exponentiation, our old friend, right? What do I mean? I mean, right, the points z and c cross such that z to the n is equal to 1. You know these guys. These are the roots of unity, right?
You want to say x gives c star a new z modular structure?
Yeah, so that's why, right? I said that out loud and I was like, C star. I won't have that problem in the Drinfeld setting. So, yeah. But then see, like the old Z module structure was not on C star. So that's why it's like the new part here is like difficult. The analogy is not perfectly tight. But at least hopefully it'll carry you through the other thing, what I want. Why do I care? Because every abelian extension of Q is contained in some cyclotomic field Q adjoins zeta n. And if you've known this theorem forever, you don't feel it's a big deal, but there are very few fields that we can do this for, right? If you give me like some other field that's not Q, an imaginary quadratic field, and you're like, construct all the abelian extensions of that field, I will be like, I hate you, right? Like, this is a big deal that we can just make these explicitly. And it's all about the torsion of this new Z module action. Like, that's how I want you to think of the exponential. The exponential gives you exponentiation, which gives you a new Z action, which gives you torsion points, which gives you interesting abelian extensions of your base field. And so that's what I will emulate with the Carlitz module. I will get a new FQ brackets T action on C infinity, and its torsion points will generate almost all, okay, so there's like a tiny caveat here, but that's easily fixed, almost all abelian extensions of FQ brackets T. And so FQ brackets T is added to the world of fields that we can do explicit class field theory for. And that is, as far as I understand it, what first motivated Carlitz to study the Carlitz module. So I will just leave you with the definition of the Carlitz exponential function so you can get started playing with it on the homework. Okay, it's in the notes, but I feel like I'm duty bound to write it down. And here, Dn is the product of a monic of degree n. So there's another analogy in the function field setting is that before I had n factorial, which was so monic is positive in the left-right world. So monic is positive because the units in Z are plus and minus 1, and the units in FQ are FQ star, so you don't want like one of each for each unit, right? Each multiple units. So you just use positive and monic on the side. Okay, and for ours, for the exponential function here, I had n factorial, so you multiply all the numbers that are less than or equal to n. Usually in the function field setting, you just multiply all the numbers, the polynomials of degree n, because there's enough of them. So that's the analogy with the exponential. And then the n up here, right, in the exponential, you shouldn't think of it as the number n, it's the absolute value of n, which here would be q to the n. right? The absolute value of a polynomial of degree n would be q to the n. So there's a pretty tight analogy between this exponential and the other exponential if you think about it. And the big proposition that we'll prove next time, but that you can use to start playing with this, is that if z is in C infinity, then EC of TZ is TEC of z plus EC of z to the q. So for the exponential function, it was easy for me to tell you the new action, right? When I multiply by n inside, I exponentiate outside. Here, I'm going to have to take it step by step. I'm first telling you if I multiply by t inside, what happens on the outside. This mess happens, right? But from there, once you can prove this, which you do directly by just playing with this power series, it's really not even that big a deal. Then you can get the action of every other polynomial, and you can get your new FQ brackets T module structure, and then you have a theorem similar to Kronecker-Weber in the classical setting. So that's where we're going. That'll be the beginning of next lecture, and then after that we'll do Drinfeld module of every rank. This is the rank 1 case. And we'll go a lot faster, and there probably won't be time for any proofs. And my time is even more than up, so thank you.